Hello, and welcome to Limits and Continuity and Algebraic Approach. So I'm going to go a little more into detail on the examples we had from the last video. So making a chart or drawing a graph is okay, absolutely. But both methods are time consuming and definitely better off with the help of technology. And the better way, as much as this hurts you to hear me say, the better way is algebra. Okay, so here we go. A closed form function is any function that can be obtained by combining constants, powers of x, exponential functions, radicals, logarithms, and trigonometric functions, and some other things that we don't enter into in this text, into a single mathematical formula by means of the usual arithmetic operations, add, subtract, multiply, and divide, at squaring powers and roots, and composition of functions. Everything except piecewise defined functions are closed form as far as this class is concerned. All right, so piecewise defined functions, special case. The rest of them, pretty much like this. Every closed form function is continuous on its domain. So if we want to know where it's continuous, we could just find its domain. Thus, if f is a closed form function and f of a is defined, the limit has to be equal to the function value at a. Also, a fact that we have used, if f of x is g of x for all x except possibly at x equals a, then the limit as x approaches a of f of x is the limit as x approaches a of g of x. And what that really says is, if you could rewrite f of x as x minus a times g of x over x minus a, and that part of the function g of x might have a ratio to it, right? It might be in the numerator and denominator. But if you could rewrite f so that its common factors multiplied by this other function, the limits of the f and the other function are going to be the same. We used this fact in the last section when we factored and canceled to try to fill in the discontinuity. So we used that fact before I told you it was a fact. Theorem. All right, so these are all the details, and we're going to do examples. If f of x has the form of f of x equals one polynomial, degree n, divided by another polynomial, degree m, just polynomial over polynomial, we can calculate the limit of f as x goes to plus or minus infinity by ignoring all powers of x except the highest in both the numerator and denominator. So basically, looking at this big old function, all we focus on is the leading terms. And the leading terms are always going to be the highest power of the numerator and the highest power of the denominator. All right. Now, here's a strategy. If a is a finite number, so not infinity, first we decide whether f is a closed form function. If not, then it's piecewise. Okay, we have to deal with what's going on there, and we'll talk about that. If it's not closed form, if it is a piecewise defined function, then we have to find the left and right limits at the values of x, where it changes from one formula to another. Right, the cut points, or cut values. If f is a closed form function, all right, anything that's not a piecewise function, try substituting x equals a in the formula. One of three things will happen. If f of a works, then we know the limit's equal to the function value, we're done. If we substitute a for x and we get 0 over 0, we need to do more work. 0 over 0 is easy. We could simplify that all day long. I know it's a weird thing to say that it's easy when we can't divide by 0. But it is 0 over 0, all good. If f of a is not defined, all right, so you don't get an answer, and it has the form k over 0, or what I mentioned in the last one, no, number over 0, then the function diverges to plus or minus infinity, and you have to check which one it is. All right, but if a is not a finite number, if the given function is a polynomial or a ratio of polynomials, we're going to use the theorem above to focus only on the highest powers of x. Right, this theorem, it says we just look at the leading values. Okay, so that's our strategy. Substitute if we can. If it works out, awesome, we're done. If we get 0 over 0, we have to do more work. If we get a number over 0, we're done. It goes to infinity. We just have to figure out if it goes up to positive or down to negative. Okay, let's calculate the limit. The limit as x approaches 0 of 2x minus 4. Now, 2x minus 4 is a closed form function. It's not a piecewise defined function at all. 0 is a finite number. In a closed form function, I'm going to substitute 0 for x. So that's 2 times 0 minus 4. 0 minus 4 is negative 4. I've found the limit to be negative 4. Similarly, 4x squared plus 1 over x is a closed form function. Negative 1 is a finite number. First thing I'm going to do is substitute. Everywhere I see an x, I'm going to put in a negative 1. And when I substitute, I put in parentheses negative 1. Take that x, just kind of break it apart. X, break it apart into parentheses. Wrong button. There we go. Parentheses negative 1. Only the x is squared, so only the negative 1 gets squared. Negative 1 squared is 1. 1 times 4 is 4. 4 plus 1 is 5. In the denominator, I have a negative 1, so 5 divided by negative 1 is negative 5. I'm finished. Now, the limit as h approaches 0 of h squared plus h over h squared plus 2h. Notice how there's an h everywhere, and if h is 0, this whole thing would give 0 over 0. So I'm going to simplify first. I take my expression, h squared plus h over h squared plus 2h. I factor in h out, right? Both terms have an h in common. What I'm left with is h plus a 1. H divided by h is 1. H squared divided by h is an h. 2h divided by h is a 2. H's cancel out. I'm left with h plus 1 over h plus 2. This is my f of x. This is my h over h times g of x. And this is g of x. Although there's no x's in here. All right, so this is approximately the same as. So I get the function h plus 1 over h plus 2. Well, now I can try 0 again. 0 plus 1 is 1. 0 plus 2 is 2. I get a limit of 1/2. All right. So in number 4, I'm looking at the limit as x approaches 0 from the right. Only from the right. I can't put in 0. 1 over 0. It's not an acceptable answer, right? A number over 0. I know that this is going to plus or minus infinity. I need to know which one. So I'm getting close to 0. I started at 0.1. I got a negative 11. At 0.01, I just evaluated. You can use Desmos or your calculator, whichever. I see the values are negative and they're getting big. So I know that it's not the positive one. It has to just be the negative value of infinity. You will never want plus or minus. Infinity is an answer. It's all you have to figure out which one it is. Okay. The limit as x approaches infinity of 6x squared plus 5x plus 100 over 3x squared minus 9. Now, our handy little theorem says, you know, when you're going to infinity, you really only need to worry about the leading terms in the numerator and denominator. The limit as x approaches infinity of 6x squared over 3x squared, well, I could simplify that. The x squareds cancel out. And 6 over 3 is 2, all right? But look at this. The limit as x approaches infinity of 6 over 3. Well, x could do whatever it wants. 6 over 3 is just hanging out here being 6 over 3. It doesn't care what x does. It doesn't have any x's in it. We canceled them all out. So if we cancel them all out, x could go to infinity, x could go to Zanzibar, x could go to El Paso for the day. It doesn't matter. There's no x's here, so my answer is just that 6/3, and we always simplify to write 2. All right, don't give me any unsimplified fractions. 12 over 2 is 6. Write it like it would be. 6 over 3 is 2. Write it like it would be. Notice this is negative infinity. So limit as x approaches negative infinity of 2x to the 4th plus 2x cubed over 1000x cubed plus 6. I could take care of the ones that are below the leading, right? The highest one, 2x to the 4th, in the numerator I keep it. the highest power, x cubed. I'll keep that 1000 x cubed in the denominator, and I'll simplify. And when I simplify, 2 over 1000 becomes 1 over 500. X to the fourth over x cubed becomes x. Now, as x goes to negative infinity, this x is going to go to negative infinity. Negative infinity over 500 is not an answer. But it does tell us a really large negative number, negative 5 billion, divided by 500. We do know that it's going to end up to a negative. And we know if the numerator keeps getting larger, denominator stays stable, the whole fraction is going to keep getting bigger. So bigger, but in a negative way. Awesome. Not a number. This is how we think about it to get the answer. All right, this limit doesn't have an x, so the numbers don't care what x does. The numbers are just the numbers. And sometimes we resort to tables rather than evaluating to see if it's a negative or a positive. All right, we want to find all points of discontinuity. This is not a closed form function. So we know that this piece is a closed form function, and we know this piece is a closed form function. So each piece is good. The only possible discontinuity is where we go from one branch to the next. So on the left, for x values less than 1, the limit as x approaches 1 from the left of f of x is the limit as x approaches 1 from the left of the 1 minus x. Right? This is left. Less than, left of. So when I substitute my 1, now it doesn't matter that I'm to the left. That left just told me which piece to choose. 1 minus 1 is 0. Okay. Now let's check the right. The limit as x approaches 1 from the right of f of x is the limit as x approaches 1 from the right of, I use this expression, x minus 1. Now that from the right just told me which expression to use, I'm only going to substitute the 1. 1 minus 1 is 0. Since the limit from the left and the limit from the right are equal, the limit exists. The limit equals f of 1 also, so it's continuous everywhere, right? Because we knew the left limit was equal to the function value. What we end up with is a graph 1 minus x, 1, bad graph. I'm going to call this left. And the right graph is x minus 1. There's 1. And we're going to call this 1 because they match up at 0. All right, so this is the right. Oh my goodness, I just did that. That's so not right. That's not correct at all. From the left, I'm only looking at values to the left of 1. So I stop there. From the right, I would actually graph here and go right. That's what our graph would look like because it has to pass the test of a function. All right, so that's what our graph looks like. And they hook up here at the cut point, so it's all good. Let's look at number 2. G of x is a 3-piece function, x cubed plus 2 if x is less than or equal to 1, negative 1. X squared if negative 1 is less than x, which is less than 0, and x if x is greater than or equal to 0. Again, x cubed plus 2, x squared, and x on their own are closed form functions. All right, so they're good on their domains. We have to focus on going from one to the next. So we'll look at for x equals negative 1, and we'll look at x equals 0. Looking at the reference value of x equals negative 1, from the left, if we approach negative 1 from the left of g of x, it's going to be this top function, left of, less than. So I'll use negative 1 in x cubed plus 2. That's going to be negative 1 plus 2, which is a 1. From the right side, literally x is to the right of negative 1 in this inequality, so x squared. We'll put negative 1 in x squared. Negative 1 squared is 1. We know the function is continuous at x equals negative 1. Fantastic. Now we'll do the exact same thing for x equals 0. The left, literally x is to the left of 0, so I'll use it here, x squared. And notice this is x is bigger than. above, larger, upper, to the right. X, when I put in 0, it turns out to be continuous at 0 everywhere. If you were to find that the limit from the left, limit Sx approaches a from the left of f of x equals 3, and maybe the limit from the right is 7, then there's a discontinuity at x equals a. And I'm sorry my examples didn't include one of those, but I like positive examples. I like to be a positive person. All right. Thanks for listening. Continuity and algebraic limits.